Yeah, hi everyone. I'm Zhao from Tsinghua University. It's really glad to see that our workshop has attracted so many audiences, but unfortunately I cannot attend in person. Yeah, I will give an overview of our autonomous driving challenge this year, and this challenge is actually a joint effort from multiple organizations. My team at Tsinghua University, Shanghai AI Lab, and Emotional. We thank all of them for their amazing works. And our challenge is actually, different organizing teams, like we discussed like around half a year ago, we all have the intentions to make some new computer vision tasks for autonomous driving. And that's why we try to put all our efforts together and we finalize 4 tracks for the challenge. The first track is called Open Lane Topology, focusing on understanding the row graph topologies given video input. And the second track is called Online HD Map Construction. The goal is that given the sensor data, we want to estimate the lane graphs with onboard sensors. And the third track is called 3D occupancy prediction, where we'll talk about very soon. And the fourth track is about planning. And within our workshop, we hosted 2 tracks of the challenge. That is the second track, Online HD Map Construction, and the third track, 3D occupancy prediction. And I would acknowledge the specific people who contributed to these challenges. For the 3D occupancy prediction challenge, we have Xiaoyu Tian, Chonghao Sima, and Wai-Kit Fong, Promotional. And for the Online HD Map Construction challenge, we have Tianyuan Zhang and Yichen Liu. Okay, I'll give a quick introduction of these tasks. First, let's talk about the 3D occupancy prediction challenge. What is 3D occupancy prediction? How about the traditional existing vision-based 3D bounding box detection representation? Why are they not enough? What are the problems with these existing 3D bounding box representation? We noticed that in datasets like Waymo open datasets and the NewSense datasets, they are in the urban areas. And there are a lot of irregularly shaped objects like these crane trucks. They have a movable arm that cannot be easily represented by a 3D bounding box. And sometimes we have also found out of vocabulary objects. We call them general objects. They cannot be extensively enumerated in our ontology tree. So they are usually not labeled in the datasets. Because of that, we want to define this new 3D occupancy prediction task so that it can represent all of them, either with irregular shape or out of vocabulary. So the task setting is that given multi-view images as input, the goal is to output occupancy state and a semantic label of each voxel in the 3D scene. Why is it interesting? Because the 3D occupancy is a general scene representation, and we only take vision input to predict the 3D detailed representation of the geometry, which is quite challenging. And based on this task, we built a dataset or a benchmark for this challenge. And the benchmark is carefully chosen. It's built on the NewSense dataset. So I want to say thanks to the Emotional team for providing the test set for this 3D occupancy task. And we also defined the voxel size to be 0.4 meters, not too small and not too large, so that more people can maybe use a single GPU to run the model for this 3D occupancy prediction task. And finally, the metric of this challenge is mean intersection over union, which is very similar to semantic segmentation. And the challenge statistics, this out of our expectation, this track becomes the most fiercely contested track. We have received submission, like more than 400 submissions from more than 140 teams from 10 countries. And we also provided a baseline performance with performance of 23.7 mean IOU. And the winner got the mean IOU of 45, which is more than doubles our baselines. And also this track is also very competitive. The top 3 performance only has a variance of 1.4 mean IOU. Okay, now let me tell you like who are the winning teams. First, the innovation award goes to the Former team from Zhejiang University, Xi'an Jiaotong University, Tsinghua University, and the Fudan University. And we have another innovation award that goes to NVOCC from NVIDIA and the Nanjing University. And then we have an honorable runner-up team, which is 42 Dot from 42 Dot Inc. And finally, the champion also goes to the NVOCC team from NVIDIA and the Nanjing University. Okay, let's give them applause, and maybe Yiming on site, you can help us to present the awards to the winning teams. And then we'll have a presentation follow up by the winning team.
Okay, so I should first present given the certificate or later?
Yeah.
Okay.
Thank you for the help.
Congratulations.
We have 2 teams, another 2 teams who are not in person here. So we'll directly move to the talk of NVOCC.
Yes, sounds great.
看我的这个应该是我的麦。Okay, can everyone hear me on the Zoom?
Maybe you can.
Well,
Yeah, they can hear you.
they can hear me. Okay, okay, great. Okay, sorry, apologies for the delay. Yeah, this is so our talk today is FBOCC 3D occupancy prediction based on forward backward view transformation. This is a joint work with Zhiqi, David, Mingsheng, Shiyi, Yang, and Jose. Yeah, so why do we care about 3D occupancy prediction? So traditionally, we are very we pay a lot of attention to 3D object detection, but 3D occupancy prediction recently emerged as an interesting task. And the advantage of doing 3D occupancy prediction is that it provides very rich world information, and these world information are necessary for the subsequent tasks such as planning and prediction. And this is necessary to achieve safe end-to-end driving. When we think about these occupancy prediction, actually there have been many prior works that address the same or similar task. For example, and they are based on different modalities. So, for example, there are works that are based on LiDAR. There are also works that consider RGB plus additional depth modality input. And finally, we have these camera-based solution, which is a camera-based occupancy prediction. The advantage of doing camera-based is that it's very convenient. It has a very low cost, but of course the task itself become more challenging because now you are trying to doing 3D perception given only 2D input, so you have to infer the depths, infer a lot of 3D information from this task. Even though 3D occupancy prediction is a slightly different task compared with 3D object detection, but all these they share a lot of similarity. And when you look at these literatures, basically they all look into BEV based bird's eye view based perception solution, and basically these two tasks are very highly correlated. So that is why prior state-of-the-art works in BEV perception actually has a lot of can inspire a lot of the architecture design in 3D occupancy prediction. So one of the so there is a rich literature about 3D object detection and BEV perception. I can't list all of them here because there is a ton of them, but I'm going to list the two most related work. Two work that are most related to our solution. The first one is BEV depth and also BEV depth. I forgot. I should also mention here. So BEV depth is basically a BEV based solution that is that try to use depth supervision to improve the performance of BEV perception. So what they do is that given the input image from multiple cameras, you use an image encoder to encode them into the image features, and these features will be used as an input to a depth net. And also these and also together with these cameras and also these input to the depths, you try to basically predict depths. You use LiDAR point to supervise these depths and use it as an additional information to try to uplifting the features, these image features from 2D domain to the 3D domain. So finally, you get a feature representation in the BEV space. These BEV space features, they are uplifted using the depth information, and the specific method that they use is something called lift splash shoot, or LSS for short. This work also came from NVIDIA, was proposed by Jonah and Sanya. So we call this kind of uplifting technique as a forward projection. And this is one example. The other example I want to give is BEV former. And BEV former basically at a very high level is a BEV perception with backward projection. The way it works is that it starts from these queries in the BEV space and back project them to the 2D camera domains using deformable attention. So this you can think of this as a backward projection. It's the other way around compared with a forward projection. So these two paradigms, actually these two, like forward projection and backward projection, if you look at the recent line of BEV works, they are predominantly used by these works. So our work is heavily inspired by these two works. So that's why I want to briefly mention here. And also there are some works I also want to mention about directly related to the occupancy prediction task. One of the work is monoSync. This is one of the early works that uses does pure camera-based occupancy prediction. And if you look at their architecture, they also have a feature uplifting module. It's called FLOSP. It's basically some variant of the orthonormal feature, orthographic feature transform, basically lifting the multi-resolution features into the 3D space. And then once they get the BEV features, they have a 3D UNet that is as a BEV encoder decoder, and basically there's a context module to try to increase the receptive field. So this is the solution, one of the solutions. The other solution, more recent solution, we want to mention is VoxFormer. So VoxFormer, we will also present this work at this year's CVPR. So VoxFormer is based on the two-stage framework with backward projection. So this formulation is very similar to BEV former. So in the first stage, we use a depth estimation network to basically try to find the sparse set of queries that are visible in the 2D space. And based on the depth, we lift this set of queries into the 3D voxel space and start with these queries and use deformable cross attention to back attend to the image features. So in this way, because this so the good thing, the logic behind this 2D two-stage design is that when we are thinking about these occupancy prediction, there are visible areas, there are invisible areas, and we should start from the visible areas first, since these parts are the easiest part and they are the most reliable part. So starting from here, prioritizing the featureization of these queries, and then use like MAE like technology to fill the missing pieces. This turns out to be highly effective and very effective for the task. So this is the idea, and of course, since this is similar to BEV former, it belongs to like using the backward projection technique. Okay, so now I will go into our proposed model design. If you look at, so just now I mentioned forward projection and backward projection. So why do we care about this projection method? It's because if you look at a typical BEV perception system in AV, this is basically a figure of a typical BEV perception system. You have multiple camera input. You encode them into features using an image encoder, and then you leave these features into BEV space. You have BEV encoder, decoder. You try to output your predictions, and you can see this 2D to 3D transformation is the unique part, is the key part of AV perception that distinguish it from the rest, like traditional 2D visual recognition. This is the part that makes it very special. And this part is also the key because it encodes all these geometric inductive biases into your system, right? So we need to design this part well. And if you delve a little bit deeper into the design, you will see that both forward projection and backward projection, they have their pros and cons. They are not perfect. Each one is not entirely perfect. So for example, the forward projection is very good that, for example, method like lift, splash, shoot. The good thing is you can encode a lot of depth information. It's very good the depth supervision works very well for method using LSS. That is why if you look at the BEV depth, they use LSS, and this depth supervision is very good for AV tasks. Even the task itself is heavily 3D oriented, right? But the bad thing is because you are starting from the camera domain, the pixel, you're shooting a ray into the BEV space. This ray in the BEV space, it doesn't spread very evenly everywhere. It spreads sparser and sparser as it goes away from the echo vehicle. That means these empty areas, their sampling frequency are low. Their sampling information are less effective, and that influences the perception of at far away from the echo vehicle. On the other hand, the good thing about this backward projection, because you are starting from query inside the BEV space, right? So your spread, the spread of these queries and all these starting points in the BEV space, they are evenly distributed, but it doesn't have a very good sense of depth. So that is why things along the same ray, they're almost like equal because they are all attending to the same feature in the 2D space. The resulting effect is that if you look at the BEV feature of this backward projection, you see actually high response along the ray. You see this ray-like pattern in the BEV space, and this undesired phenomenon causes duplicate of the object detections along the same direction here, false positive as circled out here. So this is kind of undesired. So can we combine the both method in a organic manners such that they can get the best of both worlds? The answer is yes. So we propose this called forward backward projection, and in the hope that we can use the backward projection to get additional information, to attend the image domain to get additional information for the sparse areas, while at the same time we can encode the depth supervision for this backward projection. So here's the overall design of our system. So we basically start from these image features, from image features. We use forward projection. We can get we can use forward projection to get a voxel representation, and then we can collapse our voxel representation into these flattened BEV features and use it to initialize our queries in the BEV space, and use these queries to back attend the image features using back projection. So this way, there are multiple benefits. First, in BEV format, these BEV queries, they are randomly initialized. And these randomly initialized queries, they are not as good as queries that you initialize from these voxel features, because now you have a more targeted initialization, your learning behavior is better. And second, this back back projection, as I mentioned, now during the sparse area, you can actually get more information through back projection. You actually get high resolution information, you get some other information which are beneficial. And now you actually can also get two representation. One is the BEV, the flattened BEV features from this backward projection, and the other is this voxel representation from the LSS, this type of forward projection. And then you can fuse them together into the fused voxel representation. And why do we keep this z-dimensional information? Because we notice that this z-dimension information is still pretty important for occupancy prediction, because your output prediction is 3D. So we notice that if you flatten this representation, it hurts the performance. So that's why we kept the z information. And once you get this fused occupancy prediction information, this is the head design where you have BEV space encoder, decoder, and prediction head. So what we did here is very similar to BEV depth, but because now we have a voxel prediction, now we actually we need to 3D-fy everything. So originally it's a ResNet-like architecture that takes in 2D features. Now, because you have voxel, so it's like 3D convolution. Everything is like 3D-fied. Okay, so now I talked about architecture design, and since this is a challenge, so the bag of tricks also are important here. So the first thing that we need to do also for the challenge is scaling up and pre-training. So for the scaling up part, we mostly look into the image encoder. We try to scale up this part. So these scaling up with foundation models with heavier backbones have proven time and time again that this is quite effective for 3D perception. It worked in object detection. And not surprisingly, it also worked well in 3D occupancy prediction. So we use the internal image H with more than 1 billion parameters as the image encoder, and this backbone worked really well. As you can see, it has a state-of-the-art performance, a lot of tasks, and it also gave us a very state-of-the-art performance on this occupancy prediction. But of course, there are some problems. So the Newsing data set is not very large, but you have 1B parameters, and unavoidably you have these overfitting issues. So we did something to prevent these overfitting issues. So we have a pipeline for large-scale pre-training. We first, so Newsing data is some in-domain data. You cannot fully rely on your in-domain data to do the pre-training. You have to use like data, like web data with a lot of diversity. So that's why we pre-trained the backbone first on the ImageNet 22K. And then we also use Object 365 for 2D detection pre-training. So we added the 2D object detector head and supervise the network use on the detection tasks on the Object 365. Then we go to the in-domain data for pre-training, which are the depth and semantic segmentation prediction. So here, to do this task, we actually leveraged a segment entity model, use it as an auto-labeling toolkit to auto-label the Newsing data. So we use the bounding boxes and also the LiDAR points as prompts, use them to generate the object instance mask and also the staff segmentations. We use these segmentations as a prediction, as a semantic mask, as a ground truth to supervise these image feature backbone. And additionally, we also use the depth map on the new things to supervise, to do the depth supervision. So this is the depth and segmentation pre-training part of our workflow. Okay, so now I will talk about post-processing. I think this part is the most boring part, but I will just go through it quickly. We use temporal test time augmentation. Basically, you perturb the input and try to aggregate all these predictions together. And we also use temporal information, temporal TTA, where we have for the staff classes, if the prediction of the current frame and previous frame, they both belong to the staff classes. And then the previous frame, if their locations are closer to the ego vehicle, then we average them. The intuition is because for the predictions closer to the vehicles are usually much better. So sometimes these prior frames are useful. And of course, we use the ensemble of different models. So when we are doing the ensembling, we also consider the category weight and also the model weights. So these are the post-processing steps. So here are the experimental results. So first we do a ablation study. We want to show an evolution path of how we gradually build up the performance from a baseline model to the final to a very highly performant model. So we started with we unified the setting as a ResNet 50 backbone with a certain voxel size and also the input size. Then we have different versions of the model that gradually pushes from just 23% IOU to finally 42% single model. And along this evolution path, we found that depth supervision matters, and that visible mask matters a lot for training. When you are doing the training, you should focus your loss, your training with a visible mask rather than forcing to predict a lot of the invisible areas. This part is actually quite, the philosophy here is quite similar to Voxformer. Like, do the easy part, don't try to predict the extremely hard part. That actually ruins your learning behavior. And finally, is like temporal information and other things that they also help a lot here. Yeah. And also, we show that scaling up is quite effective. So with the largest model with 1,200 parameters, we can achieve 50 to over 50% MIOU performance, and which is already, I think this number is already I think number one or maybe close to number one on the leaderboard. And finally, using ensemble. By the way, and we also did some brief study. We showed that with the BEV plus voxel, these two representations together, this BEV perception, it turns out that it helps a lot with the staff classes like Terran and also some sidewalk, these and others flat like these staff classes. So that is why. So finally, with all this ensemble, with the bag of tricks, we got a final performance of 54.19% MIOU, which ranks number one on the leaderboard. And finally, I want to share some qualitative result. So we can see that compared with our baseline BEV, that the final solution FBOCC can get a more accurate occupancy prediction for irregular objects. And we also noticed that some limitations of the benchmark. For example, because of the inconsistency between the ground truth and camera mask, even though we have a pretty good occupancy prediction result, but our evaluated MIOU is actually pretty low on this one. And this, but I think these are occasional cases, but it still shows us some insight. And then finally, I want to show this demo. I personally think there are still a lot of space to further improve on this task, even though the IOU score seems high. But I think like the temporal consistency and also like the accuracy of the prediction for longer range can be improved. So I think, I think this task itself is still pretty challenging, and we should work very harder on this one. Okay, with this, we will release our code at the following repo. And with this, I want to conclude the talk and thanks everyone again.
Yeah, any questions?
Yeah, maybe.
Yeah. So I had a question. Hi, thanks for the great talk. It's very enlightening. I had a question about the segmentation ground truth that you generate for as an input to the network. You're actually segmenting using SAM. You're segmenting the ground plane and the vehicles. I can see that, but how do you actually segment like dashed lanes, mainly dashed lanes?
I see. So I think for the I think we mainly focus on the object classes and also the staff classes, the several things that we care most about. So maybe for the I think for the dash lanes, maybe you need some other special techniques to do it. But since this one is for pre-training purpose only, and it's not for like understanding the real world topology. So dash lane is not that important here, just for this purpose.
I see. Got it. So this is only the pre-training step. The final output is only the occupancy grade, right?
Yes. This is only for pre-training, getting the representation better. Yeah.
Got it. Thank you so much.
Thank you.
Are there any other questions?
Yeah, I got a quick question. When you say you were increasing the number of parameters in your model, like which part of the model were you increasing?
So for example, like the backbone, I think you can refer to different configurations of the. We actually also tried a different other backbones, like more than just internal image, but even for the same model, they have different configurations. For example, different number of channels, wider models, like a narrower model. So something like this. Yeah.
Any final questions? Yeah, I guess we are over time already. Okay. So yeah, thank you very much. Let's thank the speaker.
We have Innovation Award, OCC Transformer, and I will play their recorded video.
Hello, everyone. I'm Liu Jian from Harbin Institute of Technology. Our team secured the fifth position in the 3D augmented prediction challenge, and we are honored to have received the Innovation Award. Now, I would like to introduce our competition solution to all of you. Title of our technical report is OCC Transformer, improving CVPR for 3D camera-only augmented prediction. I will present our approach in three aspects: improvement to the baseline model, our innovations contributions, identification result and number, and the experiment result. First, let's discuss the improvements we made to the baseline model. The task, given 6 surrounding camera reports, predict 3D voxel semantic neighbors. I believe the essence of the problem is the system depth estimation interpretation. Depth estimation is crucial. And during the early exploration phase, we carefully compare different methods from 2D to 3D method. Initially, we used the monosense framework and compare 4 methods: flow steps, LS, and UV formal. We conducted this comparison results using a map. Among these methods, UV formal has points on. So we later switched to the competition baseline and made improvements based on that. We start with 3 tablets: data, model, and the node. For the data part, we tried several data augmentation strategies and found that cutout is effective for this part. In the model part, we attempted to increase the model capacity, replace the model image backbone with a stronger one, enhance the number of histories reps in the PV model, and add a 3D unit head to the decoder. In the node part, we also incorporated camera mask during the training process and found that it significantly improved the result. Later, we add the depth node as well. Next, let me introduce the second part, which we believe is a particularly innovation aspect, the fusion of detection result. The occupancy model's predictions is habits accuracy in class leveling, which can be illustrated through 2 examples. The first example is an object that combines multiple classes. The second example is the space between the classes is sticking together. Fortunately, the issues can be rectified by delivering the results from detection models. Directly using the results from the 3D detection model may not be ideal due to 2 main issues. First, detection box is rectangular. Detection report the box position is not accurate. This issue indicates that relying solely on the results from detection models may not provide optimal solutions. It is important to consider these limitations and explore alternative approaches to address it. We have made multiple attempts. First attempt involved using multitasking learning, where we train the detection and the prediction task together. However, we found that this did not significantly improve the result. The second attempt involved replacing the dynamic classes within funny boxes. Unfortunately, this leads to rigorous performance. Finally, we decided to promote the prediction detection PD box, funny box into occupancy results and perform a probability average number. This approach effectively improves the result. So the specific method we use. First, we select high confidence funny boxes. Second, generate point clouds based on the body boxes in the equal coordinate system. Select the points within the body boxes. Thirdly, convert these points into voxels. Finally, assign the probability score to the point that is within the grid range. Let's present our experimental results. Due to limited resources, we initially validated the effectiveness of our tricks on a small model. In the end, we discovered that using the depth node resulted in a significant improvement performance. We apply all the applicable tricks to a large model and achieve the satisfactory performance improvement. After all, we proceed with modern example. Firstly, we perform example by different image backbone within the same framework, which result in a noticeable performance boost. This approach was developed extensively. We utilize different test models, such as PV-, Graph-C transformer. So the inverting performance of these models was not have compared to example techniques. We still observe improvement in overall performance. Finally, we implement detection example, which shows significant benefits, particularly for dynamic studies. We observe that the gains were even more pronounced for small objects. Our final ranking was 5th place. We hope to continue diving deeper into this field and make further innovations breakthroughs in the future. Thank you for your listening.
Okay. And the honorable runner-up award goes to 42 Inc. Let me share your screen first, and then you can take a photo.
Congratulations.
Hello everyone, this is the important remaining this time. In this presentation, we would like to introduce our solution for occupancy prediction challenge in CVPR 2023 multi-contract workshop. The title of my presentation is Below Multi-Just Learning with Localization Ambiguity Suppression for Occupancy Prediction. The task is to predict occupancy state in symmetric label for a also increased rate given multi-view images. A baseline model equals that party will consist of 3 main components: an image encoder to extract image features, a view transformer to transform 2 features into 3 features, and an occupancy encoder to produce occupancy prediction. We propose several improvements on the baseline. We propose very in-depth investment for task energy and short-term supervision signal for a network component. We propose localization in UNT fraction for occupancy prediction requirement. We extend our short spatial pivot only to 3D tasks for better occupancy prediction results. We address data imbalance problem. And finally, we employ other techniques for performance improvement. Perspective semantic supervision is aligned into image encoder. In particular, we use a time ambient feature level and fit it into 2 rectangle blocks followed by a predictor. Since the image level semantic annotation are not available, we project 3D level clouds with label into the image to get semantic annotation on the image, which is used to train the semantic branch. Moreover, via perspective semantic supervision, we provide each network component a short path to supervision signal, which help training the network become easier. Occupancy prediction is then prediction task would require incorporation of large context. We extend a short spatial unit point for 2D tasks to learn 3D feature to different something bed and field view. In addition, we propose localization ambiguity suppression to define occupancy prediction. Unlike an system, the presence of object can be predefined by detected particles from 2D sensor. In a camera system, we need to localize 2D objects from images. This is to localization in distant and small objects. We propose to suppress low conflict vision using statistical trial. We also address data intelligence problem. As shown in the figure, the portion of common classes is nearly 10,000 times higher than rare classes. To address this problem, we employ weighted cross entropy and dice. We also employ other cognitive for performance improvements, such as high resolution input, long-term temporal, technical argumentation, pseudo labeling, and more. For our experiment, we use ResNet 15 as our baseline entry. 24 we use 16 GPU I100 to train our model in about 3 days. Here are our experiment results. The baseline model achieved 33.5% MIOU. Here we show performance improvement. We added different cognitive, including perspective, semantic supervision, class and loss, customized architecture, ASCP3D, high resolution input, long-term temporal, procedural labeling, test argumentation, localization, ambiguity suppression, stronger backbone, and finally, model example. Our final model achieved 52.45% MIQ on display, and we win second place in the open simulation challenge. This is the end of my presentation. More information is available on the technical report. Thank you.
Okay, so let's end the awards of the occupancy prediction. And Han, can you start with the HD map construction challenge?
Yes. Cool. Well, hi everybody, welcome back. And yeah, let me introduce the second track that we are hosting, online HD map construction. As we know, for autonomous driving, having a structured representation of the road is very important for our self-driving system. For example, the lanes, the traffic lights. There are two classical ways to obtain them. The first one is that we try to get it from the human annotated high definition maps. The second one is lane detection. But what are the problems with lane detection? We found that the lane detection only applies to easy scenarios like highways or very simple urban driving. And for lane detection, we only care about very few categories, like the lane on my left, the lane on my right, and that's it. And the third problem with lane detection is that the detection in a camera view is hard to be translated into bird's eye view for the downstream task of prediction and planning. That's why we care about this task, online HD map construction, where the inputs are multi-view images and the output are vectorized map in the 3D space. And based on this task, we build a benchmark on top of the Argo2 datasets, Argoverse 2 datasets. And within this benchmark, we have around 1,000 scenes, and the input are 7 cameras. The cameras images, as you can see on the right, they have different resolutions and different, one of the forward camera is even in a different pose. And taking these camera images as input, we aim to estimate 3 categories, like the lanes, the road boundaries, and the pedestrian crossings. Our evaluation metrics are chamfer distance and average precision based on different recalls. This is also a very fiercely contested track. We have received more than 500 submissions from more than 40 teams from 3 countries. And we have got impressive champion performance. Our baseline was 42 mean AP, and our champion got the mean AP of 43.5, which is almost doubles the performance of our baseline. Okay, finally, let me announce the challenge winners. First, the innovation award goes to the match team and the Xi'an Jiaotong University. And the honorable runner-up goes to MapNext team. This team does not want to reveal their affiliation. And finally, the champion also goes to the match team and the Xi'an Jiaotong University. Okay, let's give them a round of applause and welcome the winner talk from the match team. I think they will present online. Let me end my screen share.
Are they joining the Zoom meeting?
Yeah, are you online?
Yes, yes.
Cool.
Well, hello everyone. I'm Wenjie from MatchDrive. Here, I would like to share our solution for online high-definition map construction, which won the first place in this track. I will first introduce the data processing techniques and the model architectures, and then briefly introduce the BMapNet, which provide many useful ideas and experience for our task. The goal of this task is to extract accurate vectorized local map from surrounding images, which are usually captured by on-vehicle cameras. The word vectorized here means that the map elements are represented by ordered point sequence instead of the rasterized pixels. It's a natural choice to design a deep neural network for this task. And the question is how to effectively model the vectorized local map in the neural network. Here is our solution. The map elements, including path crossings, lane dividers, and road boundaries, are uniformly represented by an ordered sequence of key points. We can see that in the original annotation, the sequence direction is random, which brings ambiguity to the model training. So we reordered the points from up to bottom and from left to right, followed a consistent principle, which greatly reduces this ambiguity. Besides, we noticed that there are many redundant points which contribute little to the line shape. Therefore, for compact map construction, we adopt polyline simplification methods such as RDP and VW algorithm, and we remove the redundant points to form the compact contours. As is shown in the table, the compression greatly reduces the point number without losing any expression performance. Well, we present the model architecture in this slide. The pipeline can be roughly divided into four parts, including bird-eye view extractor, temporal fusion module, query-based point decoder, and point mask coupling head. Given surrounding images, we first generate range view features through a backbone. Then a bird-eye view feature extractor aggregates and transforms the image features to the unified bird-eye view features. To utilize the geometrical prior, we adopt a deformable attention-based network and encode the camera parameters, including the intrinsics and the extrinsics in the fixed reference points. To further leverage the temporal information, we devise a temporal fusion module. This module fuses the new bird-eye view feature with that of the hidden state using vehicle eagle pose, and the hidden state is updated for the next frame. Finally, the instance decoder decodes point features and instance masks. The query is point ones and a set of point queries are aggregated to form a single instance feature. We obtain the corresponding instance masks by matrix multiplication between the instance features and the bird-eye view features. In the final submission, the results of complex shaped lane boundaries are from the point regression, and those of the simple shaped like path crossing and the lane divider are thinned from the masks. Here are some other improvements. Replacing swing tiny by internal image backbone, we improve the performance by around 3%. We also explore the image augmentation methods, including the rotation, random cropping, flipping, and grid masking. For more supervision, we adopt semantic level, instance level, and range view mask-based loss functions. Multimodal and multi-epoch ensembles are also adopted. The offline hard mining is utilized to further enhance the performance on hard samples. For more technical details, please kindly refer to the tech report. This table shows the model performance. We achieve 83.5 in mean average precision and surpassing the roundup by around 10%. Even with the tiny model, we achieve around 75% in mean average precision. Next, I would like to introduce the BMapNet, which provides a strong baseline for our challenge solution. BMapNet models map elements as piecewise Bezier curves and predicts the control points. Multiple novel modules are proposed in this task, including the piecewise Bezier modeling, point curve region loss, and the position encoding align module. BMapNet predicts the coordinates of control points first, and then the Bezier curve is recovered by the definition. This slide shows 3 pieces and 3 degrees of Bezier curve. In this case, we require 10 control points to represent the curve. The gray points here on the line is the explicit control points, which we directly get it from the prediction, and the orange points are implicit control points, and and is obtained by the regression of the offset. Well, here is the architecture, which is consistent with the pipeline of our challenge solution. Based on the ideas and experience of BMapNet, we achieve high performance in the online map construction track. Well, that's all for the presentation, and thanks everyone for listening.
Thank you, Wenjie, for the great presentation.
Okay.
Okay, if there's no question.